if you are within perturbation theory, this means that the overall correction to all the physical observables will be small on increasing the power. Okay? Now, let's see how things work in this case. Now, I really want to determine the effect of, so what I want to do is not to compute the eigenfunction, but I would like to compute only the eigenvalues. Now, I have a question. So, if you look at this potential, can you tell me if the first order correction, so we just saw that first order correction is something like phi 0 of n v phi 0 of n. Okay? This is E1 of n. Now, can you tell me if in this particular case E1 is 0 or is different from 0?
It's not 0.
No, it's 0. So just try to find out why is it 0. Why it is 0.
Sorry, which case again?
So I want to know if you consider the correction, I mean the cubic correction. What is the, so what is the, I'm saying that E1, the first order correction to the energy, will always be 0. Can you explain me why I'm stating this?
I think you will eventually use ladder operators, I think.
Oh, right. If I do the calculation, then I will find it 0. But do you know why it is 0? So can you give me an argument without computing it? So let me write this using the coordinate representation. I will have something like dx v of x times phi 0 n of x modulus squared, right?
It's an odd integral, I think.
Very good. So you see that this term here, by symmetry, the wave functions are, so the probabilities are always an even function of x, while the potential is an odd function of x. So this integral is always 0. So by symmetry, okay, a cubic potential will not introduce any shift. So this is 0. So what we want to compute is the second order correction. And as you said, what we have to do is, so what is convenient to do is just write this term here using destruction and creation operators. Okay? And this is equal to minus lambda omega over 2h2 A plus A dagger. Sorry. This is the harmonic oscillator length, okay? So such that we just have something similar, symbol to compute. So we get A plus A dagger to the power cube, okay? So this is equal to minus lambda omega 2 square root of 2 of A cube plus A dagger cube plus all terms. Now, do you remember that the second order correction to the eigenenergies was m different from n of E 0 n minus E 0 m, and then I have the probability phi 0 of m v phi 0 of n modulus squared. So let's consider the state n, okay? So if I consider the eigenstate n, E n will have at 0 order h, sorry, I forgot h bar omega n plus 1/2, okay? Then we said the first order correction is 0, so the thing we have to do is to compute the second order correction. Now, the first question I would like to ask you is, can you tell me how many terms in this sum should be considered?
Up to the power of 6?
No.
No.
Be careful. No, right, maybe correct. So I want to know, so I should consider n plus 1. So I have to do a sum with n different from n. So I should consider n plus 1, yes or no?
n plus 1? Yes.
N plus 2?
Sorry, is it m or n?
So what I want to know, I have to sum over m, okay? And m different from n, we said I have to consider n plus 1, n plus 2, n plus 3. So, do I need to consider n plus 4? So,
No.
yes?
No, I think no.
Sorry, how to know if you have to consider it?
Sorry?
How to know which values we have to consider?
This is my question for you. So I have to compute these matrix elements. Now, this matrix element may be different from 0 or equal 0. Now, given that I wrote you this term here, so if you want I can write everything. So I just write the full expression so that you see it, okay? So, let me copy it. Plus 3 n a dagger plus 3 n plus 1 a. Okay? So this is the perturbation. There is a cube, a dagger cube, and a dagger and n a. So the matrix element between, so let me write it here, between phi 0 of n and phi 0 of n plus 4 is different from 0 or is equal to 0?
Is equal to 0.
Why?
Because the a makes the wave function become a square, a power 3 lower down the.
So here you have, so it's correct. So here you have at most 3 creation operators. Okay? So if you apply to n a dagger cube, at most you will have components which are proportional to n plus 3.
Yeah.
Okay? But there is no way in which you can have a component n plus 4. Okay?
Yeah.
So now tell me, who asked me the question? Is this clear?
Yes, I understand.
Okay. So let's stop for a moment.
Professor,
Yeah.
we are only considering the case for n plus 1 to n plus 3 because of the creation operator. What about the annihilation operator? So
Yes.
we do not have to consider.
No, I did not finish yet. Now, since we have annihilation operator, then we also have to go to n minus 1, n minus 2, and n minus 3. Okay? Okay. Okay? Then I have another question. If I consider the matrix element between n and n plus 2, is it 0 or is it non-zero?
I think it's 0
Why?
because the wave function is on the same order and it has different n and
Yeah. So you can see here there are only cubic terms and linear terms. So if you want to connect the wave function n to the wave function n plus 2 or n minus 2, then here you should have had a dagger square or a square. Okay? Is it okay? Now, you have to, so at the end, here out of this sum, this infinite sum, you have only 4 terms that you have to consider. N plus 1, n minus 1, n plus 3, and n minus 3. Okay? Now, you know the rules to compute this matrix element, okay? So you have to compute matrix element of this kind, and a cube n plus 3. This type of thing. So you have coefficients, you put everything together, and I give you the result. Okay? So just do the calculation yourself. But this symbol, I want to discuss the result. The result is the following. Assuming that you did the calculation correctly, you get that En is equal to omega n plus 1/2 minus 15 lambda square omega over 4 square minus 7 lambda square omega divided by 16 plus higher order correction. So, I want to know, can you tell me when do you think perturbation expansion is valid? Do you think it's valid? So, what is the condition that lambda should obey such that perturbation theory is valid?
Lambda is small and greater than 0.
What does it mean small?
The perturbation is small.
What does it mean perturbation is small?
I think ignoring higher orders of lambda.
Sorry?
Yeah.
Okay, I do not hear. Can you repeat?
I think the perturbation may be valid when we ignore the high orders of lambda.
Yeah, but let's say, do you see any danger here? So is it valid for any n?
No, as you said earlier.
No, but from this expression. Just look at this expression. Well, you see, earlier I could have said something completely wrong. Okay? Now you have to check if what I told you earlier is correct or not. And I would like to know if you see where what I said earlier appears.
Professor,
Yes?
can you repeat the question we have to answer? Like, what really are you asking?
So what I'm asking is that, so suppose that you have fixed lambda. You have lambda 10 to the minus 2, okay? Can you tell me if what we found is valid for any n? Or not?
Professor, you mean valid as in the expression for the energy makes sense?
Yes.
Um,
So what I want to say is that, yes, so the expression is correct, mathematically correct. But there is something which tells that it cannot be applied for any n. Can you tell me why?
the expression goes like powers of n, so
Very good. So you see that here n scales like n squared. So even if you fix a small lambda, whatever, at some point there will be n large enough such that this correction is not anymore small as compared to the previous one. You can see something in a more clear way. So this thing is in a clear way, but just looking at the gap. Okay? So let's look at En minus 1. So we know that for an harmonic oscillator, as you said, the gap is independent on n. So it's just omega. Okay? So if you combine these two, then you will get 1 minus 15 over 2, I'm just counting, but lambda square n. Now, you see that the gap, so whatever you fix lambda, at some point, the correction will become of the same order of the zero order term. And this is nonsense, because this, for instance, will predict that the lowest level will go, so when this becomes negative, that there is a crossing, that something which was below then goes an energy higher than, so the two levels are exchanged. This is nonsense in the sense that we started by assuming that perturbation was small, and we derived some formulas that are applicable only in this limit. So the resulting expression should obey this initial hypothesis. This means that what should be small is not, 15 over 2 is a number, okay? But it's not really lambda that should be small. It should be small lambda square times n. So 15 over 2 lambda square times n should be much smaller than 1.
Professor?
Yes.
What about the n squared term?
So I'm taking the gap. So the gap I have to do from this term, I have n plus 3/2 squared minus n plus 1/2 squared. So the n squared term disappears.
Okay.
Okay? So this is the energy difference between neighboring levels. Okay?
Yes.
So, as I repeat, the thing that should be small is this, 15 over 2 lambda square over n. Now, physically, what happened? What does it mean? Sorry. It means what I tried to illustrate before. So if you have a quadratic potential and you just add a cubic potential on one side, then basically the correction will be huge. Because you go from confining potential to just something which goes to minus infinity. So if you go higher in energy in the spectrum, the quadratic potential will tell you that the wave functions are localized. But the true potential says that they are not localized because, there is no confining. It goes to minus infinity. And so you are doing something completely wrong. Now you see that the smaller is lambda, the larger number of levels from 0 up to a certain value you can consider by perturbation theory. you can see it in this way. So you see that if you have a potential of this kind, if the lambda is small, then it will be something like this. So this correction will go down at higher value of the potential, okay? So this means that if lambda is more, then you have more levels that you can consider in perturbation theory. Okay? Now, this is what you have to reproduce. In addition, you have to do a second exercise. The second exercise, you have to consider a perturbation which is not anymore cubic, but is quadratic. You just add lambda, omega, x over L fourth. So it's anharmonic potential, okay? But it's not x cube, but it's x4. So the procedure is the same as before, but you see that for an anharmonic potential of this kind, basically what happens is that you will get something like this. So close, you get a steeper potential, okay, more or less. So again here, I really would like to understand, so you just do the calculation, and I would like to see correction up to the second order. Now, in this case, the first order correction will be non-zero, okay, by symmetry. With x cube, by symmetry, you could say, look, is 0, but with x fourth, it will be non-zero. So you will get correction to the first order and correction to the second order. And in particular, something I would like to ask you to verify is what are the constraints on perturbation expansion? So I want to know what is the value of lambda. So does lambda will depend on n, so is perturbation expansion. So you have to tell me when perturbation expansion is valid or not. Okay? So in the x cube case, we found out that actually it should be lambda squared times n, that should be much smaller than 1. I really would like to understand what is the condition for x to the fourth. Clear?
Sorry, can you repeat just now what you say, because the connection was down for a while.
Okay, so from where should I start?
I think after you're telling us about you're asking about the constraint of perturbation expansion.
No, that's it. So I want to know just, so you just compute the correction to the nth level. Now you have x to the fourth, so most probably you will have terms which are connecting n to n plus 4, okay? So you have only 8 terms. So you have to verify if there are some matrix element at 0 or non-zero, And the next thing I really would like, the next thing I would like to know if perturbation theory is valid provided that lambda is smaller than 1, is smaller than whatever. Okay? So you have to tell me, I did this calculation and the calculation is valid when this expression is smaller than, much smaller than 1. Okay?
So it's like the lambda squared n you just mentioned in the Q potential.
Do I know? No, but it's not obvious that it should be lambda squared times n.
Oh, I mean, it should be similar to that. I mean,
The idea is similar, so you have to find some expression that should be much smaller than 1 such that the perturbation theory is valid. Yes. But it's not at all obvious that it should be lambda squared times n. I don't know, okay? Now, let's stop here for a moment. So I have a question. So, do you want to discuss briefly the exercises I gave you or not?
May want.
Yeah, I
Yes.
think it will be good.
Okay, so last half an hour we discussed the exercises. But you should tell me which exercise I gave you because I don't remember. Okay? So can you
I
tell
think
me?
it's the density matrix.
No, right, I remember the
There are
density.
3 exercises.
Yes, but I don't remember which one. Can you tell me?
So the first one is to calculate the average value of angular momentum Jz with the density matrix a quarter, and you have the first element to second element.
Okay, yes, just no. Yes.
And then the second one is
No, let's do it one. So let's do this, okay? So the density matrix was this one, rho equal to 1/4 2 1 1 1 1 0 1 0 1, right? Right? Say yes.
Yes.
Okay. So the first thing you have to verify is that the trace, so the density matrix is a density matrix, okay? So the trace is 1, so this is okay. Then the next thing is if it's admission, it's yes, okay? So rho is equal to rho dagger. Now, and what is the third? Should be positive definite. So for that you have to compute the eigenvalues. Okay. Now the eigenvalues, I mean, you have just to compute minus lambda. Sorry, so I write minus lambda identity, minus lambda, and minus lambda, okay? And so you have 1 minus lambda times 2 minus lambda times 1 minus lambda minus 2 equal to 0, okay? And so you can verify that these are all positive eigenvalues. Okay?
Sorry, do you have the values of to verify?
Sorry?
Do you have the eigenvalues to
And this you can do it yourself.
No?
No, yes, this is a quadratic equation, so you can solve it yourself.
Yes, please. I need just to verify our results.
No, this you have to be able to verify yourself. You are grown enough that you just do it 24 times and you verify if this is correct or not. Okay? So I'm confident you will manage. Okay? Now, if you verify that this is positive definite, then the trace, the average value of Jz is just nothing but the trace of rho Jz. But Jz is what? It's something like 1, 0, minus 1. 0, 0, 0, 0, 0. Okay? So you have to do the trace over just the multiplication of these two matrices. Okay? So actually it will be just the value of rho in 1, 1 minus the value of rho in 2, 2. Because here you have just the diagonal 1, 0, minus 1. So you get 2 minus 1 and you get, which is 1 times 1/4, and you get 1/4. Okay?
Sorry, I went away for a while.
Okay.
When it is out.
Okay. So do you have questions or not?
Yes. What's the resulting number that you obtain?
I don't give it to you. I mean, you should not ask for the solution of a quadratic equation. Okay? This is, otherwise I would treat you like two just young students. You are grown up. You are grown up. So a quadratic equation you can solve it. You can just take. Okay.
Yeah.
So we have to discuss.
I already calculated. I just want to check whether my result is correct.
Yes, it is correct. No, I don't know, but okay. Tell me. So what is that? Yes. Yeah.
The final results. Can you give us the final result?
Of what?
The base of this?
Yeah. So it's 1/4 because.
1/4.
Yeah. But why it's look. Why it's 1/4? Because you have rho 1, 1 on this row n times a diagonal matrix is just rho 1, 1 minus rho 1, 4. Sorry, rho 1, 1 minus rho 3, 3. Okay, sorry, I have to close because there is a noise. Okay? Now, there were other exercises, but I don't know.
The other exercise is you wrote the expansion of psi, which is the alpha spin up, and beta spin down, gamma spin down, spin up, and delta spin down, and then you give us
yes.
of the probability equal to 1. And you ask what is the form of rho A, and also you said to us to find coefficients such that rho A equals to half of the identity.
Okay. Now, let's see. So you have the state psi is equal to alpha, what is up, right? Plus beta, what was beta? I forgot.
Up, down.
Down, down,
Up, down.
up, down. Okay. Plus gamma, down, up. Okay. Plus delta, down, down. Okay? So the rho is just psi, psi. Now, question, did you manage or not?
Okay. Yes.
Sorry, it's rho A. We asked you.
What? No, I do not hear very well. Can you
Rho A, not rho. Maybe the professor want to calculate rho first.
yes, but let's say I want to first consider rho, okay? Do you know what is rho or, so you did not calculate it?
And directly calculate rho A. So.
Okay, very good. So, rho A is equal to, so let me say, it's the trace over B of rho, okay? So, you should have computed rho, I think, okay? So, you have to trace over the second indices, okay? So this means that, so for instance, so let me say, I just write this way. So I have up B of rho, up B plus down B of rho, down B. Do you agree with this or?
Yes, it's true.
Okay. So rho will have terms which will contain all possible things. Then you have to just make this scalar product, and then what you get is something like this: alpha square plus gamma square beta squared plus delta squared alpha beta star plus gamma delta star, and here there is a complex conjugate. Okay?
Professor.
Yeah?
Actually, I obtained alpha plus beta squared, alpha squared plus beta squared, and gamma squared plus delta squared.
But okay, then probably what I wrote. Okay, so if you wrote this, then probably I just wrote because I did not check on my notes, so probably I just gave you a different state. So you get alpha squared plus beta squared.
Yes.
I think you're right. Okay. Just a moment. Let me check. You're right. Yes. In this notation, I here have a different state. Sorry. When I wrote, so you're right. So here I have alpha squared plus beta squared. Okay. Here you have gamma squared plus delta squared. Here.
Yes.
Yeah. Gamma square plus delta square, and Now here you have alpha gamma.
Alpha gamma plus
Yeah.
beta delta.
Yeah, just simply alpha gamma plus beta delta, and here is the complex conjugate. Okay?
Yes.
Very good. Well, now the conditions are simple. Then you have to put this is equal to 0 and this equal to 1/2. The diagonal component equal to 1/2, right? Okay? And then you have to solve this. Alpha square plus beta square is equal to 1/2, and then you have gamma square plus delta square is equal to 1/2, and then you have alpha gamma star plus beta delta star equals 0, and of course there is the other. So also the complex conjugate. So the real and imaginary part of this should be equal to 0, okay? Okay. So you can verify that so basically, in order to cancel these terms, okay, so basically what you need to have is that, for instance, just a moment. Sorry, I'm reading, but I have a different notation. So now I'm trying to recall with this, with what I wrote on the blackboard. Just a moment. Yeah. So you can solve this and this by just equating, for instance, alpha is equal to plus minus delta, okay? And the same is true for gamma and beta. So it turns out that the result that you get is there are 4 terms which have this property. Actually, there are many more, but at least, so for instance, just assume that all these coefficients are real, okay, to start with. You will get that the terms which have this property are plus minus, down, up. So, just for the moment, for the sake, you just take all the coefficients real. Okay? So you can take, for instance, alpha equal gamma, beta equal delta, and then, or alpha equal beta and gamma equal delta. Okay? And by this condition, then you find that they should be equal to 1 over square root of 2. And you generate by just equating to 0, then you generate all possible combination or up plus down plus minus down down if they are real, or up down and down up. Let me do that. I mean, I don't know if this is clear, but let's take this. Alpha gamma plus beta there is something I'm not, just a moment.
I think we
Sorry. Just a moment. Sorry, I'm just doing something wrong. So, to solve this equation, you can take alpha equal delta equal 0. Okay? So this is automatically satisfied. So this goes to 0, and then beta and gamma are 1 over square root of 2. Okay? So alpha equal delta to 0 means that you are taking up down plus down up, and you get this term here. Okay? With a plus minus sign. But you can also have also terms of alpha.
Sorry?
Yes?
Why did you choose alpha equal to beta equal to 0?
it's just one case.
This one case. I'm trying to make this term vanish. Okay? So if I put alpha and delta equal 0, then this is okay. Then I can take gamma and delta equal 0. Okay? And then I generate this term here.
You mean beta and gamma?
Sorry?
You mean beta and gamma equal to 0, that
Yes.
will generate the first term and the first line?
Yes. Then I have also cases in which I take alpha and beta equal 0. But then the state, sorry?
I need to repeat the condition to get the first one. Why up and down?
In order to get up and down, then beta and gamma should be equal to 0. Okay?
Yes.
So this term disappears, and beta and gamma are just 1 over square root of 2.
Professor, I have a question. I think that we cannot solve exactly the solution of them because I think we lack conditions for them. For example, we can take, like, in general, alpha, beta, gamma, and delta can be complex number. So each one will have 2 variables. So four of them will have 8 variables. But in fact, we just have three equations. We cannot solve exactly 8 variables with 3 equations.
Now, just a moment. Let's go step by step, okay? I'm considering for the moment the case in which these are real, okay? Hello?
Yeah, for the case
in which they are real,
constraint easily.
you can solve the constraint easily. Okay? Hello?
Sorry. Can you hear me?
Actually, I'm still in doubt with that because if it's real, we just have three equations.
Okay, let's do it. Okay?
But 4 variables.
Okay, let's do it. No, because there is normalization condition. If you, oh, sorry. Shall we do it for alpha beta real? Let's do it. So I have alpha squared plus beta squared equal 1. Then I have gamma squared plus delta squared equal 1. Alpha gamma plus beta delta equals 0. Okay? And this is the same as before. Moreover, I know that alpha square plus beta square plus gamma square plus delta square should be equal to 1, right?
I think that condition is even like not strict than the two equations that you have wrote. I mean,
What?
it's
No,
the final equations is even is meaningless in this case because we already have two stricter conditions.
Oh, sorry, Professor. You wrote the wrong equation. I think alpha squared plus beta squared is 1 over 2.
sorry, it's 1 over 2, sorry, yes.
But I mean, what I mean is the final equations.
Which one? Is this final? Sorry, just a moment.
No.
This
the
one?
condition that you have just wrote.
This one? No, just go. Is this one you mean?
Yes, this
This
one.
is this is the normalization condition.
But I mean, it has no meaning in this case because we already have alpha squared plus beta squared equal to 1.
Right, I agree, but I agree.
Yeah, so,
Okay.
yeah, in general, we just have
Okay,
three conditions.
so, yes. So, this equation, you can solve it by saying alpha equal 0 and, I cancel the states, okay? I think it was delta equals 0. Okay? As you said, this is automatically satisfied by this relation, okay? Because this comes from normalization, but then the diagonal comes from the fact that the trace of the density metric should be 1, and this is automatically satisfied, right?
Yeah.
Okay. So, in order to satisfy this relation, okay, then you have several possible solutions, okay?
Yes.
Right. So now you see that alpha equals 0 is equal, so alpha equal delta equals 0 is one solution, gamma equal beta equals 0 is another solution, okay? Then you have other possibilities like alpha equal beta equals 0, okay? But this is not possible, okay? So what we are saying is that I want to check if there are more solutions such that beta delta is equal to minus alpha gamma. This is what you want to say, right? I'm asking you a question, so hello?
Yes, what?
No, I think so. Lelian, I'm asking a question. So, do you agree that these are solutions that satisfy the condition?
But I mean, there's no definite solution because we have infinite solution in this case, I think.
Right, because you may have, you can verify that if these are
What
real.
I want to say,
No.
overall, what I want to say finally is because we have 4 variables and just 3 conditions, so we cannot find out.
No, but this is not, sorry. I think, so this is a nonlinear equation, so it's not linear. So this fact is, if you have real coefficient, this is the only possibility that you have.
Professor?
Yeah.
But I think there are still more conditions. Like if I take a real, I take values like maybe I have a half minus a half of those the alphabet, I still get the zeros.
Try to do it, and you will see that the trace, you will get a separable state. So the density matrix is not the one we are looking for.
Okay.
So what I want to say is that, So for instance, if you take beta equals 0, so if you take other conditions, then, so these are the only 4 states that satisfy this relation. Of course, what you say is correct in the sense that if the coefficients are complex, there are many other states. So for instance, if you take up plus e to the i5 down, okay, normalized, then this is not true anymore. Sorry, this is still true also with this. So you have infinite, you may add phases, and these are possible solutions. Okay?
I think it's plus minus.
Huh?
You have the plus.
Yeah, you have many more. You may have, but plus minus is just having a different phase shifted by pi. Okay? So if you put a minus sign, it means that you're just putting a phase plus pi. Okay?
Yes.
So these are, so if you take real, these are the only 4 possibilities. Then you have combination. So something that you can verify is that, for instance, if the weight, you need to have similar weights. Okay. Okay, sorry, yes, you're right. Now I understand what you said. Okay, so let me add the following. Right. Now I understand, sorry, I'm slow. So I understand what you wanted to say. So these are 4 solutions, okay? The solution that I wrote is 1 square root of 2 up plus minus down, okay? And 1 over square root of 2 down, up, plus minus, up, down. Let's consider real cases for the moment, okay? Now, in principle, I can do just a rotation on the first spin or on the second spin. Okay, so now I realize that the exercise was more difficult than I thought. If I do a rotation on the first bit or on the second, So for instance, then I will still generate a state with this property, okay? So,
Sorry, with what property?
the trace is that the reduced density matrix is proportional to the identity. Okay?
Okay.
So, to answer to the question, you are right. Okay? So, and I realized that I was not clear enough in giving you the assignment. So, I think it is enough to find at least some states that verify, but it's true that the condition that I wrote, this one, generate an infinite number of states. What are those states? Now, those states are the following. These states have a name. They're called Bell states. Bell states from the name of a physicist. It's not Jingle Bell. Bell is now all the states that have these properties, they are generated by doing rotation on the single spins. Okay? And this is well, this gets complicated, so you don't need to do it. There was a third exercise. Or do you have other question on this?
We taking part with this sort of invalid question.
What does it mean invalid?
I mean that because we have infinite conditions, I mean solutions.
No, let's say this is a good question. Then I mean it was much more difficult than I thought. Well, I did not pay much. So I was going to be happy if you would find the condition. So if you find the conditions, then I mean I was thinking that I was happy if you would just get the condition. But to find the full solution, yeah, it's getting complicated. So the question is that did you get up to here?
Yes, yes.
Okay. There was a third exercise or not?
Yes.
Which was?
Did I read it for you?
Sorry, Professor.
Yeah?
Maybe we have to stop because of the time of lunch and we can correct it next time.
Okay, that's a good, the best.
We don't have time.
Okay, so let's stop and go for lunch. I'll